So last day, if you can remember these three major steps we have in any machine learning end-to-end project, we have completed the data processing part. We have, went through some calculations on the evaluation of any machine learning model. And from today onwards, we were about to start about building the model, right? So building the model means actually we will go through various machine learning algorithms by which we can create some model for prediction of some new data or something like that. Okay. So already you have an idea that what are the different types of algorithm can be. Like what I mean to say is that there are some classification type of algorithm, there is some regression type of algorithm, and many something like this. So what we will do, we will start with regression type of algorithm first, and then we will move for classification. Okay. So we will start with what we call linear regression. Okay. So let's start. You see, just assume a scenario is that you have a set of points given as an example, and it's something like what you can see here. Okay, let me get this pen. No, not pen. This highlighted. Okay, so what you can see here is that these dots that you can see is at the different points with respect to is like we have some input and some output, and assume that we have only one input and only one output. Okay, so input is x and output is y. For every x there is some y. Now if you just put the x corresponding to y as a dot, I mean as a point in a 2D plane, it will be scattered dots, right? Something like this. If you don't have this particular line, just forget about this valid line for time being. Just assume that we have these dots only, and on the using these dots, you see, you can basically see some pattern present, that somehow pattern in the sense some relation which making between x and y by these dots. So basically, the through regression we will try to capture this pattern as close as possible. Okay, now since we are talking about a 2D 2D plane, so naturally in a 2D plane, if you have a lot of dots, and if you want to make a pattern with a on the using the on the dots, the best way or the easiest way that you can do, that you can try to make a straight line, right? Because it is on a 2D plane, right? So that's why it's given over here that given a set of input x and output y, data define, I mean output y data define a straight line that can best represent the linear relationship among x and y. So before we start linear regression, one thing should be clear to you, that we can apply linear regression only when we are sure that there is some linear relationship between the variables x and y, where y is called dependent variable and x is called independent variable, because x is input. Okay, so naturally we all know what is the equation of a straight line. It's something like this, right? Y equal to x mx plus c. Now you see, definitely you will say that it is not possible to draw a straight line on each and every dot. Then it will not be a straight line, it will be some curve, some scattered straight line, right? But here my intention is not to touch each and every points. Here you see, the question is written that straight line that can best represent the linear relationship. not optimal represent. I mean optimal in the sense not each and every point has to be correct. So now if I tell you to draw a straight line in this particular plot, definitely you can draw straight line in this form, in this way, or in this way. Any direction straight line is possible, but all the straight lines is not representing the best relationship, right? The relationship between x and y in a best way. Only one of them will represent. So that is what actually you have to find out, that which exact straight line is representing the linear relationship of x and y in a best way. And when we are talking about straight line, definitely this M and C will come in the scenario, because this is the two things by which actually any straight line is adjusted, right? One represents slope and another represents the intercept, right? That's why you see I have written here that it is not possible to touch each and every point by a straight line. We always try to draw the straight line that can give least average error between the actual and predicted y. What does it mean? What is actual and predicted y? You see, just imagine a situation that this point represents an actual data point, right? Represents, so somehow, for example, this corresponding to this point, it touches the x-axis here. So for assume that the value of x-axis here is 2. Similarly, in the y-axis, say the value is, say for example, 3. So for value x, the actual y is 3. But with respect to the straight line, if you see, if you draw the straight line on x, it will not be 3, maybe it will be 3.7. So what is the difference between the actual y and the predicted y based on the straight line is 0.7. In the same way, for each and every dot, we will have some error between actual and a predicted. Sometimes error is huge, sometimes error is very low. As a whole, what we have to do? Our motivation will be to minimize this average error somehow. So let's see how we can do that. Here very interesting point comes. Just see this scenario. So before you understand the what is drawn over here, just see the 3 points. These 3 points is actually the steps by which we can do the do our task. So what we will do, we will start with an arbitrary value of m and c, because we don't know exactly what should be the x-axis, what should be the straight line. So any straight line is represented by two variables, m and c, right? So we don't know what is value of m and what is value of c. That is what actually you have to find out. So that's why we will start with some arbitrary m and c. If we have some arbitrary m and c, and because of that, definitely we will get some straight line, right? If we have a straight line, we will get some average error for each and every points on the 2D plane. And as I told you that our intention will be try to minimize the error in every iteration. So in the left hand side, what you can see is exactly the diagram that we have seen in the previous slide. In the right hand side, what you can see is actually it will show you how you are minimizing the errors by changing the straight line's direction and orientation. So that's why in the right hand side, as you can see here, the y-axis is giving the error and x-axis is giving a weight. Weight means the variables on which the straight line depends. The orientation of the straight line depends. So here the weight means the intercept and the slope, that is m and c. So basically both m and c cannot be represented by a single diagram. for m we will have a diagram like this, for c we will have a diagram like this, but in general this weight w is representing similar form of m and c. Okay, so let's start with, so if we start with any arbitrary value of m and c, maybe you will find your initial straight line is something like this, but definitely this is not representing the pattern of the data in proper way that I can see here. So what basically we will do, as I told you, that for each and every axis we will find what is the corresponding y, and similarly we have the data in our side that for each and every axis what is the actual y, and we will find a difference. I mean, and difference for each and every points, make an average. Somehow we will try to minimize that. How we will minimize that you will understand it later, but try to understand that assume the average error is present somewhere here in this situation. So it has some value. I've not written any particular value here. Maybe average error is 20 or 2000, whatever. Some average error is here, something like this. As you can see, this y-axis representing error. That means this error E should go down as we will move forward for the next iteration, right? So this is iteration 1, you can assume in this way. In the next iteration, somehow I should update the value of m and c in such a way so that this straight line will get much closer than the pattern of the points. Maybe next time it will be something like this, it will become a little more closer, and you see the error that what you had here has minimized a bit, right? Next time it becomes more closer, error minimized little more. Next time it again more closer. Still you see the error is actually decreasing towards zero, right? Because this is 0. Now you see it's more close again, and maybe this is what the optimal straight line that we wanted, where error is very less. You see I have not given error is equal to 0 because if error is 0 that will be an ideal case, that generally doesn't happen. So if error has to be 0, it means that each and every point has to be in exactly in straight line form, which generally doesn't happen. So you will never find error is 0, you will find something very less than, maybe very close to 0, maybe 0.05, maybe 0.001, something like that. So basically our intention will be to minimize this error as close to 0 as possible. That's the thing. But remember, you will say that I have started from this side. Why this side is present? This side is present reason is that you don't know exactly the value of the weight will be from this side or this side. So you see, this W is range from 0 to any some value. Similarly, error ranges from 0 to some value. This value of W can be in this side, also can be in this side as an initial, right? So naturally, when you will basically start your journey for minimizing the error, maybe your ball or this particular error may start from this side or may start from this side, but whatever, it has to go downwards and come back here, right? So now question is that what is the benefit we can get from here? Ultimately, after drawing this straight line, what benefit we have got? The benefit is that assume I want to know some particular value of y for some x whose value is not present in the dataset. For example, some x over here whose value is not present in the dataset. But since I have this straight line, I can see that for this particular x based on the straight line like y equal to mx plus c, if you put the value of x in that straight line equation, you know what is m and c because you have optimally got this straight line, right? So by the value of m and c, on putting value some x, you can predict the corresponding y, and that is what actually you require. Because if you, when you are creating a model, you are creating the model based on some set of values, but that is not the only values present in the whole, in the universe. There are many more values beyond that. But what benefit we can get, that if I can represent a linear relationship between the input and output using the same linear relationship, I can predict at least what should be the output for some other values which is not present in my training dataset. That is what benefit we can get. So what we can see here, that this particular, this ball which is representing the error is actually going downwards, right? But remember, what is the direction of the slope? Direction of the slope is, just an opposite side, right? So that means what actually you were doing, your error is actually going exactly opposite to the slope's direction, right? Remember this point. This point will be useful when we will try to evaluate, try to not evaluate, try to derive the equation by which we are actually minimizing this value of m and c. Okay, so let's try to understand that. Now you see, the question is that how to get this best estimate of m and c, and you see, we will start with the equation of the error, as I told you. So what is the equation of error? Equation of the error, not error, actually it should be average error, as I told you, should be something like this, that 1 by n summation over I equal to 0 to n within bracket yi minus yi cap square. What is this? First of all, what is n? This n is the total number of data points. For example, 10 or 100 or 1000, whatever. And what is yi? This I is actually representing, you see, from 0 to n. It means all the data points. So I is representing the ith data point. Okay. So what is yi? That means this yi is nothing but the actual y of the ith data, and yi cap is the predicted y by the straight line. Okay, and we have a difference. Now question is that you can ask me that why this squared? The squared is like, this square is because first thing is that it will be easier when we will do the some mathematics on this, first of all. Second point is that if you have some value, say actual value 3, and you have got value 7, so 3 minus 7 is minus 4, right? Similarly, for example, actual value is 5 and you have got 1, so 5 minus 4 is 4. In both cases, we have a deviation of 4 from the actual value. But if you add these two directly, then minus 4 and plus 4 will cancel out and it will show no error. But that is not true. That's why we make it squared, so that whatever, whatever equation, the result that we will get will always positive. There will be no chance for cancelling one with other. Okay. So now you see, since I told you that yi cap is nothing but the predicted y, and this predicted y depends upon the corresponding m and c that I have got, right? That's why you see this, instead of predicted y, I have written mxi plus c, because this m and this c, this is what actually we are trying to find out, right? And other part remains same. So I hope this equation is clear to you. So this is a equation of error, and what I am trying to do, I am trying to minimize this error e by, I have two parameters here. I have to minimize e with respect to m as well as with respect to c, right? So basically, what we have to do? We have to find out how much, how the derivative of this error we are getting with this m, and see individually. And why this derivative? The reason is that you see the derivative represents how you are decreasing, how you are changing your error, right? That's why derivation is important. So if I go for the derivation of error with respect to m, what will be the equation? You see, remember, I'm trying to derive, I'm trying to make a derivative with respect to m. So in this equation, wherever m is present, it's very easy. I think derivative, all we know that we can find out a simple, multiplication rule over here. That is, first of all, this 2 will comes out here, so it's become 2 by n, right? Summation of I equal to 0 to n for all the i's I'm saying doing. Now see, this derivative of error, this particular part, if you see only this part, yi minus mxi plus c, this part here, we will have a partial differentiation that we all know. So that is actually you have done here. You see that ddm of this multiplied by this one, right? And if I do this, if I continue this partial differentiation, as a result, what we will get? d by dm, dm, I mean derivative of error with respect to m, we will get minus m multiplied by yi minus mxi plus c. Why minus m? Because you see, if you find the derivative of yi with respect to m, this is basically 0, because actual output is not anyhow related with m. There is no relation between this yi and m, right? Yi is not a function of m. So naturally, this yi is acting like a constant for this derivative of m, right? So it's 0 minus, so this part is 0 minus this part is left, and here c is again constant because I am trying to find the derivative with respect to m. So c is a constant, so it's also 0. What is only thing? mxi. So ddm of mxi. So naturally it will be minus m, right? So now you see, so this is what your formula for the derivative of error with respect to m. So, and this is what you can say gradient of the error with respect to m, that you can represent at delta m. Similarly, what we will do, we will try to do the derivative of error with respect to c in the same way. And if you try to do the thing, what will happen? We will just have a change of, instead of m it will be c, not exactly the same formula, but it will be something like this. If you try to do it by in your home, you will see that the derivative of error with respect to c will look something like this. Okay, and this is what we can represent by delta c. Okay, so this is what important, you need to find this delta m and delta c, because this is something that basically it's need to be changed in each and every iteration. So let's do one thing. Let's see how we can, what should be the steps of, writing the program or writing the code for, doing, the linear regression, or sorry, linear regression. Yeah, linear regression. The first thing is that we must have these two equations. What is this? M new. M new means this new and old, just representing two, value of m into different timestamp. Initially, there was some value of m. In the next time, the value of m will be updated. So naturally, that has been represented by m new. Now you see what is written here: m new equal to m old plus eta into delta m. Similarly, same thing for c. Question is that what is this eta? This eta is called learning rate. What is learning rate? This learning rate is extremely vital in any machine learning, training. It's like, for example, if you try to understand the importance of learning rate in a very, layman term, you can imagine in a sense, like, for example, you have a subject in your engineering career, maybe, or maybe some other somewhere else. Suppose that you will have a course of 6 months. Okay, 6 months course, and there is a teacher who will teach you the subjects fully in that 6 month. But unfortunately, because of some reason, suppose you have got only 2 months. What will happen? Within 2 months, the teacher will teach you the whole syllabus, which is supposed to be completed in 6 months. So naturally, the speed of teaching, also in your side, the speed of learning should be very high, right? But you know, is it really good for you? Like, for example, in any subject, for example, data structure. If you teach data structure in a single week, the full data structure subject, is it possible to learn fully, correctly, everything? Not possible. Really not possible. So that means high learning rate is not expected. And this basically harms the learning strategy. Similarly, suppose you are learning data structure for a year, entire year, very slowly. What will happen? You know, it will take a lot of time to learn that particular subject, which is again not expected. So this value of learning rate is similar, as this example in machine learning algorithm also. In machine learning algorithm also, you just imagine the model is, that is what basically you. The model has to learn not very quickly and not very slowly, somewhere in between that. So based on, this learning rate, how good a model will learn, that will vary. Okay, just like as you can see, like if you go back to the previous slide here, as you can see, you started from this point and it jumped here. So from this point you jumped this here in a single iteration. As you can see, for example, I have only 5 or 6 iterations here, like it was 1 2 3 4 5 6. Within 6 iterations you have got this straight line, but it's not, maybe the exact scenario. But if I, just for timing, if you think, so we have only 6 iterations to get the optimal result. But it may not be, a situation, like sometimes it needs more time. It needs more time means more iterations, and more iteration means from one point to another point it will not jump very, with a very large distance. It will cover very small distance, and one by one, and at the end finally it will uh, reach to the uh, optimal error, something like that. Or if you have a very large learning rate, then what will happen? Say for example, you were here, next time you will be here, next time you will be here, next time from learning you will basically cross the, optimal error part, and you will go this side naturally, because you are doing it very, you are taking very quick learning strategy. So naturally, you just assume a situation that you are jumping from this position to this position directly, then next time this position to this position directly. Naturally, next time you will cross the minimum one and go this side, and after coming here, then model will decide, you will see that no, again we have an error. So again it will jump from here to this side, but it will again cross, because learning rate is very high. So what will happen, if your learning rate is very high, you will keep on, oscillating in between these two sides and never reach to the optimal error. So your algorithm will never converge. That is the problem will happen if you have a very high learning rate. And if you have a very small learning rate, then what will happen? You start journey from here, and it will take lot of iteration to come here only. So it will take lot of time to come to the optimal one. So it's very time consuming learning it will be, which is again not expected. So basically what exactly the learning rate will be, that's not possible to express. That depends upon problems, that depends upon the types of data. So that's a part of, you can say, up trial and error. Basically what basically most of the people does, like they start with learning rate 0.01. Okay, maybe they vary from 0.001 to 0.1, and somewhere in this particular value a good enough learning rate can be found out. Okay, so and this learning rate is actually, this concept is present in everywhere. So it's not only for linear regression, I'm saying for each and any machine learning algorithm, wherever learning is there, it has to have some learning rate. Okay, anyway, let's go to the steps. So you see, we started from this here because we know that there is no changes here right now. Fine, we will compute some error. So it's a very abstract level of steps I have written here. Okay, and if this error is greater than the threshold, so that means lot of error is there, so I must go for another iteration. Then you see, go 5, it will go 5 means actually compute this delta m and delta c by the equation already you have seen. So equation is not very tough, right? It's just like you have to calculate with respect to data and the predicted value. Then you will compute the error, and then from the computer again you see line 4. Line 4 means checking if error is e is greater than threshold or not. If it again greater than threshold, again this delta m delta c will be computed, error will be computed, and again come, and once this particular criteria will be false, then it will not go to 5, it will come into else part, it will go to 9. 9 means actually it ends. So your learning completed, and here you have designed a model. Okay, so this is what basically we have learned, is what we call gradient descent algorithm. Why it's called gradient descent? Because we are going through the gradient of error and we are descending down against the gradient of error. So that's why the name is gradient descent. It's an optimization algorithm which basically optimizes the error between the actual output and a predicted output in successive iterations. Now, using this gradient descent algorithm, we can implement linear regression. Okay, so let's do one thing. This is the theory part that we have understood. Let's do one thing. Let's go back to the code again. Okay, let's go back to a Python code and let's see how to write the code for this gradient descent algorithm for implementing linear regression in Python.